Welcome to After Hours Engineering, Episode 4, RISC-V Softcore. In this episode, we finished looking at the RISC-V's base instruction set, the branch and the jumps. In addition, we'll look further into the load and stores and how they access memory and loading of the registries. So let's go. For the branch and the jumps, we are looking at two Swizzler type instructions, and we'll talk about that in a minute. But they're structured like this. This is the branch immediate and the jump immediate. So we'll start with the branch types first. If we scroll here, we can see that the opcode is still in the same place. RS1 and RS2 are still in their same columns, as well as the function 3 is. However, the immediate positions are all jumbled up in positioning. This is swizzling. And if we come down here to the diagram we have here, you can see that this is where we talk about the produced versus the immediate value. This row right here is the produced value, but it isn't what goes into the instruction. We have to take and pull out various bits of it and swizzle them into the position into the instruction itself. And I've labeled the numbers as to where they're coming from. And we always drop off the lower bit because we're half byte aligned on the branch type instructions. All the branch instructions, they take the program counter plus the immediate, and if the function turns out to be true, we then take the branch. Otherwise, we continue to the next instruction. This is like it is on many other processors. So this is one of the instructions. All the branches are the swizzling type instructions. So when you are creating the instruction itself, the first thing you do is calculate your branch address as a produced value, and then you swizzle it into the instruction. And that's what you have here. And of course you can, in the hardware, we'll do the exact opposite and unswizzle it to get the actual branch that we're going to add. The immediate value we'll add to the PC. If we come down here, this is the assembly format for the instruction. We have our two operands that we'll operate with, and then the destination or the branch offset. An example that we show here in the instruction is if we're going to offset by C or 1100, we create the produced value first, which includes the 0011 that we have down here. And then once that's produced, we can throw off the last bit and then swizzle in the other bits into position. And that's the branch on equal. And again, as a repeat, we talked about the volume 1 and looking at figure 2's comment. It's very important that we consider being produced rather than the bit position within the instructions immediate field. And that's what they were talking about in the figure, is this kind of swizzling. The jump and link instruction is very similar in that it also swizzles its bits into position. You can see that they're all jumbled up here. We have our opcode and the destination register, and then along here is the offset itself. It's the same kind of thing. If I was to show you a diagram, it would be pulling out bits out of a produced value and moving them into swizzling them into their position on the immediate fields here. So that's the branch and the jump type instructions. Let's revisit the load and stores. So we have our load instruction right here. This is the load byte unassigned, and we control that using the function. We specify the byte size that we're going to load and whether it's signed or unsigned. We have the usual opcode, the destination that we're loading into, and then a base address with an immediate added on. And that's what you see here. In this example, 8A is being added to the X16, the value that is in X16. That specifies our address to where the byte is located. Because it's a byte, there shouldn't be a misalignment. The loads and the stores are adhere to what's called natural alignment, which is based off of the size of the data that's being moved and not the instruction, which should be aligned to the word. So in this case, we're loading a byte unsigned, which means we ignore the sign bit. This doesn't actually represent a sign for us. We interpret it as non-signed, and we load it straight into X19 and fill in the rest of the register with zeros, which pretty much wipes out any of the data that's in there. We've literally loaded a single byte into a 32-bit register. The load byte is the signed version, and it will look and interpret that upper bit on the byte and fill in the top with ones. So now it's been sign extended into the register. And that's what this immediate does, is it allows us to grab a byte. In this case, you could do a load half word, and now you're referencing the top and the bottom 2 bytes, or 2 bytes up here. But again, it could be all over the place in memory relative to what the value x16 is. And again, with the RISC-V, you can use the load upper immediate to adjust the x16 register with an add instruction and be able to access all of memory using that technique. It's a multi-instruction approach. So if we go to the stores, again, I've put in the little verb here in the manual that talks about naturally aligned to the reference type. The store operates pretty much the same thing. We're taking a value out of one of our registers here specified by RS2, and we're putting it into an address. And then again, this is all based off of the offset, and RS1 being that base address. And then we can store bytes or half words or an entire word based on these types of instructions: store byte, store half word, or store word. The offset can be looked at as the 2 last bits of it, but it's really not. If your offset happens to be, in this case, a store byte, your offset could be a 0, 1, 2, or 3, and whatever RS1 is pointing to as a base, you can select which one of the bytes you're pulling that data from. So in effect, it could turn the last 2 bits into the offset into it. But offset can be any value much larger than 3 or 4 instructions. So that's how the load and bytes work. They are operating off of naturally aligned references versus the instructions, which are operating off of aligned concepts, and exceptions could be thrown if you try to access an instruction that is not aligned properly. And that's it. Okay, we just did a speed run on the RV32i base instruction set, but how do we go about implementing them? Well, in the next episode, we'll step back and take a high-level look at the big picture, with the goal of creating a mental map of where we need to go. So until next time, peace.